Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1967. The intellectual landscape of mathematics harbored a perennial challenge, a conjecture known as Fermat's last theorem. This statement, a deceptively simple expression of the impossibility of finding whole number solutions for the equation a to the power of n plus b to the power of n equals c to the power of n, when n is greater than 2, had captivated and confounded mathematicians for over 3 centuries. While various attempts to prove it arose, a complete and universally accepted proof remained elusive. This was the backdrop against which a young mathematician, Andrew John Wiles, would begin a journey that would culminate in a monumental achievement, albeit decades later. The focus of this analysis is not the ultimate proof itself, but the intellectual groundwork that preceded it, the pivotal 1967 work by Wiles that began a path to his eventual triumph. The genesis of Wiles' work lay in a convergence of seemingly disparate areas of mathematics, primarily the theory of elliptic curves and modular forms. Elliptic curves, defined by cubic equations, possessed a rich geometric structure and exhibited fascinating arithmetic properties. Modular forms, on the other hand, are complex valued functions exhibiting specific symmetry and transformation behaviors, especially when subjected to linear fractional transformations. The connection between these domains, established in the latter half of the 20th century, would prove to be crucial to the ultimate resolution of Fermat's last theorem. The specific contribution of Wiles, in 1967, while a preliminary exploration, provided a vital building block. It offered an early insight into the relationship between elliptic curves and modular forms, while the full extent of the Shimura-Taniyama conjecture, which proposed a profound connection between the two, was yet to be fully understood and formalized. Wiles' research helped shape an understanding of how they were related. The Shimura-Taniyama conjecture proposed that every elliptic curve over the rational numbers is modular. A modular elliptic curve is an elliptic curve which has a corresponding modular form. At their core, these two mathematical objects, seemingly unrelated, possessed an unexpectedly deep connection. The central tenet concerned the possibility of associating an elliptic curve with a modular form. The proof of this was the work that Wiles undertook, albeit decades later. His work in 1967, while incomplete in its aim of proving Fermat's last theorem directly, laid the foundation for the methods he developed later. It provided a framework for understanding the arithmetic properties of elliptic curves, notably their relation to modular forms through the lens of Galois representations. Galois representations, a tool that maps the Galois group of a field extension to a group of matrices, became central in Wiles' later argument. He used these representations to encode important arithmetic information within the language of modular forms. This approach offered a new perspective on the problem, allowing mathematicians to translate the arithmetic properties of elliptic curves into questions about modular forms. The immediate impact of Wiles' 1967 work was, in its context, quiet, reflecting the nascent stage of the field. Its direct application at the time was therefore limited. However, it spurred a wave of interest in the Shimura-Taniyama conjecture. It acted as a stimulus for further intensive research in the mathematical community. The conjecture, once a relatively obscure area, gained momentum. As researchers delved deeper into the intricacies, they realized that proof of the conjecture would have far-reaching implications. The subsequent evolution of Wiles' work is a testament to the power of persistence and the collaborative nature of mathematics. The development of modularity theorems, the central pillar in the proof of Fermat's last theorem, involved the efforts of many mathematicians. Contributions from Kenneth Ribet, who proved that if the Shimura-Taniyama conjecture were to hold, Fermat's last theorem must also be true, placed a large emphasis on the importance of modularity. Ribet's work provided a crucial link, transferring Fermat's last theorem to a study of modular forms and elliptic curves. This work demonstrated that any counterexample to Fermat's last theorem would imply a counterexample to the Shimura-Taniyama conjecture. Wiles, inspired by these developments, dedicated himself to the monumental task of proving the Shimura-Taniyama conjecture for a specific class of elliptic curves. His efforts culminated in work that was completed in 1994, after 6 years of solitary research. His initial proof, however, contained a gap, a small technical problem that required further refinement. With the help of Richard Taylor, Wiles addressed this gap, and, in 1995, published a revised and complete proof. This proof was not directly the work of 1967, but it built on his early work by establishing the modularity theorem for semi-stable elliptic curves a crucial step towards the complete verification of the Shimura-Taniyama conjecture. The work achieved a long-standing ambition of the wider mathematical community. The reception to Wiles' achievement transcended purely academic circles. The proof of Fermat's last theorem was viewed as a paradigm shift. It showcased the power of modern number theory. The achievement unified different areas of mathematics, including elliptic curves, modular forms, Galois representations, and Iwasawa theory. The proof's complexity was initially met with both awe and bewilderment. While the initial proof was complex, its impact ensured its acceptance. The problem, in its simplicity, became the culmination of centuries of mathematical progress. The direct influence of Wiles' work on others is easily seen in the surge of research in related areas. Researchers explored the modularity theorem in more detail, investigating its applications to other problems in number theory. The techniques used were extended to study the Langlands program, a vast network of conjectures. The Langlands program aims to generalize the connection between different areas of mathematics. Wiles' success provided a template for approaching other deep problems. His use of Galois representations and modularity, for example, inspired a new generation of mathematicians. The influence of Wiles' 1967 work, while preliminary in its time, is undeniable. It foreshadowed the profound depth of the interplay between elliptic curves and modular forms. It provided a crucial early exploration and paved the path for decades of research. This laid the groundwork for the crucial insights that led to the proof of Fermat's last theorem. Wiles' work, in its entirety, serves as a testament to the power of perseverance and the beauty of mathematical inquiry, a legacy of intellectual achievement that continues to resonate within the field today.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.